Hello and welcome to the Side One YouTube channel. My name is Ray, and in this video, part 3 of the MR4 robot, we are looking at the Arduino code, and I'll also have a quick look at some Python code as well, so we can actually have a look at what's going on. So I've created this routine called Local Mapper, and its sole purpose in life is to control the ultrasonic sensor on the servo or on the front of the robot. This ultrasonic sensor, as you would have seen in the last video, in a housing is mounted on a servo, which is mounted on a plate in the robot and allows the robot to rotate the sensor so it can see the range. For this, on the Arduino Uno, I'm using the ultrasonic sensor library and the servo library. So I've defined my pins here. I have my right servo pin, which is my right track motor. It's a continuous rotation servo. I won't be using that in this video. Same with the left servo, which is the continuous rotation servo on the left side. I have my servo sensor servo, which is this one, which is on pin 8. And I have my sensor trigger and echo for the ultrasonic sensor itself. I've also defined here the max range of 500 centimeters or 5 meters or 5,000 millimeters if you like. My sensor start position is at 0. The end is 180. That's the full range of that servo. And I've actually defined 180 positions. That means this is going to do a ping at every degree in its range. My sensor home is 90 degrees. That will be facing straight forward. The arc width is the width at which the ping will travel out and come back. So we're looking at a 5-degree width approximately. That may need fine tuning down the track. Sensor window steps. Now, because it's going out in a 5-degree arc, if we're looking more towards one side, it's possible that it will just clip the edge of an object that's only relatively narrow, and that was more to try and increase the resolution further out. I may or may not do away with that at this stage. And sensor samples. This is how many pings it will do before it moves on to the next angle. So we create our ultrasonic object, is the best way to describe that, and we're going to create our 3 servo objects. So we have to specify the trigger pin and the echo pin and our timeout. We have a ping array of positions. This is one that will be used, but I haven't used yet in my code. And I can't remember what the mag sensor value was. It's probably because I'm planning on adding some more sensors to this down the track. So the next thing we're doing is I'm creating a routine called ping US. So this is actually supposed to be ping microseconds. It's basically we are taking a range of samples. So in this case, it's 8 sensor samples as defined in our defines. We are defining some variables we're going to use further on, and it's going to also give us the max range and the min range. You'll note that I've actually set these fairly max range of 0, which is very low, and a min range of 1,000, which is very high. This is because after the first ping, these will be made equal, and then as each reading is taken, it'll give us a range of each ping that we get. Now this is for a single direction. It is not for every direction. So this is actually allowing us to get our average ping. We've got a maximum ping time, and max ping time is if it was going out to 5 meters, how long is our ping going to be? It's in microseconds, so 58 times our max range. And then we run our range collection. So we actually read the ultrasonic sensor. That triggers it to do transmit. So trigger the ping, and it times for the return. When it gets a return signal, it returns that value to range sample, which is an array that we defined up here, which is based on the number of samples we're taking. Then we'll do a delay, the max ping time minus the actual range we got back times 6. And that's to make sure that if we have an object that's relatively close, so if we have an object that's, say, here, it's relatively narrow, the ping may reflect off it and be detected, but that ping will still travel out and come back. And if we start our next ping before that echo returns, then we can actually get a false reading. And I had a lot of trouble with that when I was doing my early development. Okay, so moving on down the code, we're going to check and see what our max and min range is. If the sample is greater than or less than the max and min range, we are going to adjust those. If the value is valid, we will add it to our average, and then we'll return our average. It is important that we get our average right, because that's what we're going to be using. So we do multiple pings and get an average, and that helps eliminate some of the noise that we can get in our system. Okay, so moving on down to the next routine I've created, and that's the scan itself. So in the scan, it will actually, starting at 0 pos, it'll scan all the way through to 180 and come back. And so that's all this will be doing, and then we're going to go back the other way as well. So we're scanning each way. Our setup routine is quite straightforward. That routine also does our print, so it's printing our position in degrees, and it prints a range. It also performs a delay, which allows time for the servo to get into the new position. So in setup, we start our serial, because we're going to need the serial when we're experimenting. That's going to go through to the computer, and we'll use Python to read that. We'll make sure we've got our servos all attached correctly. The rest of it was from early debugging, sending through extra information, but that was confusing my Python code, so I've removed that. And this is very simple code. We call a scan, then we wait a second. Okay, so that's been uploaded, and now when I plug in the battery to the servo, you can see the servo head is now scanning. So this is 0 all the way through to 180. Okay, so let's look at the Python code. So this is my Python code. I did actually find another YouTuber who did a series on writing code for Python to talk to the Arduino and using the ultrasonic. His code initially didn't work for me, and I've actually looked at a couple of other sites as well to figure out how it all works, but I have used most of the code from that first one, and I just can't remember his name now. So what we're going to do is we're going to import time, and then from matplot library or lib, we're going to import PyPlot as PLT, import the rest of the Matplot library. We need NumPy because we're going to do some maths. We'll import that as MP. We need serial so that we can talk to the serial port, the USB serial, and actually get data from the the Arduino. And we're also importing keyboard so that we can actually capture the keyboard for the quit command. The first thing we're going to do is configure serial using the serial library. In this case, I'm using COM port 5. If you use a copy of this code, you will need to set that to whatever COM port your Arduino is connected to. The baud rate matches the baud rate within the serial setup that I did in the Arduino, and everything else matches that as well. So we've got a byte size of 8, a timeout of 2, and 1 stop bit. Now the next bits are a little bit more interesting. They're to do with the plot that we're going to do. So fig equals plot PLT, which is a Matplot library's plotting routine. Figure, face, cover, and K. We create a canvas manager. We don't forget to pack it all, or pack forget. So we're getting rid of the toolbar because we don't need it. And we're making sure we're going to plot our fig manager and in the window, so zoomed in to that window. So a lot of this is all to do with that. Look, this is stuff that I have only just started learning and I'm not very familiar with at all. I don't envisage this being used a lot in the end. I am doing this in PyCharm. But what I will do is I will run this. This isn't going to run like that, but it is running. And let me bring this up. And this is what we're getting from our Arduino as it runs. Okay, so what you can't see through the video feed is over the way it's over in this area. What we have is Fred and a wall, and some of my recording gear and power supply gear. Facing more forward and around, we've got a wall at a distance, and there is a table which it sometimes picks up. So we can see that this is actually working. The next thing I need to try and do is work out where there are different lines and make more sense of this. But before we can start mapping with this, as in creating a map that we can use for object avoidance, we do need to get an orientation for the robot. At the moment, the robot doesn't know which way it's facing. So if I change the direction that the robot is facing here, it's got no way of knowing. And you can see that that plot is very different on our display. So I'm actually quite happy with how this has come out. The Python code is only a temporary thing. It won't be used in the end, but we may be able to get data out of it later. I do need to make it Wi-Fi at some point. I may even put a Raspberry Pi on this to actually do the rest of it. In the next video, I hope to add a small magnetic sensor, which looks like this. This is a 3-axis magnetic sensor, effectively working as a compass, so we can use that to work out what the orientation is. And I'll add an IMU 6050 as well, so we can pick up the movement as well. Well, that'll do for this video. If you like these videos, don't forget to click on like, subscribe, and ring the notification bell. It's a form of support that helps the channel a great deal and costs you absolutely nothing. If you'd like to help the channel further, I do have a Patreon account, and you can join my long-term patrons, VIPs, Go Lucky and Lorenz Berger, and my builder patron, Al Morales 45, in helping to support the channel. If you've got any questions, either leave a comment below or drop into the Discord and ask your question there. Either myself or someone else will be able to answer your questions, hopefully. And we'll see you in the next video.